Welcome to this NPTEL lecture on techniques and principles of modern radar systems. We have seen various technological aspects of radar. Now, I take you to the initial classes where we said that to have any engineering study of any system like radar, we need a model. That model we that time introduced as radar range equation. So, this you can see is the radar range equation. We will revisit that to have that model more realistic, because that is the engineering way. We have started with a simplified model, we have described all the techniques with respect to the model. Now, I will say that if you calculate the maximum range from these parameters of a radar system, many times we do not get the correct result. Why? Because you see there are several points here. One thing is the RCS. RCS of a target is not a fixed quantity, actually it is a fluctuating things, because actually as when we studied RCS, we saw that it embodies the scattering by the target, then that thing in the environment, that signal echo signal gets transmitted. So, environment also models that. So, various times the atmosphere is different, suppose in rainy season or in cloudy weather or in severe storm, the atmospheric thing is not same. So, the RCS of any target, that will also have that fluctuation, but here we are keeping a that is fixed. So, that is one part. So, I will write that what are the problems with this model, that sigma is not constant, this is one thing. Then another part is this the receiver sensitivity S mean. Now, receiver sensitivity is also dynamically changing, because now suppose receiver has been heated, it is operating for some time. So, the noise will pick up. So, that time receiver sensitivity will go down. So, let me write that S mean is not constant. Okay. Then also you see that in this whole expression we are assuming losses, there are no losses apart from the spreading loss, that all those R square, R 4, that term, but apart from that there are no losses in the system, but every electronic system will have at least the thermal noise. So, there will be some losses due to that, etc. So, I will say losses are absent, losses are absent in the model. Then I already said that radar signal transmission, reception, everything depends on propagation effects of atmosphere, etc. So, all this actually influences, and our model should account for that. That is why we want to revisit the model. Also, I want to say one thing, that this sigma not a constant, S mean not a constant, etc. So, actually every time the whole thing is changing. So, we can say that these are something like a statistical thing. Also, noise is there, which is a statistical phenomena. We know that noise cannot be represented by any analytic function or by any tabular function. I do not know what is its value, etc. For deterministic signal also I do not know the value, but the thing is deterministic signal I have the expression, it will always fit there, etc. But for noise or these random processes, statistical processes, this is not true. So, some amount of statistical we need to find, and also we want to say that whether a target will be detected or not, that we should have a statistical measure for that, because the noise etcetera they are statistically changing. So, my answer that whether there is a target or not, that should also be a statistical, it should depends on statistical techniques. So, that means when I am saying that okay, radar has detected a target, I may fail also. So, there will be some cases when I will fail, also when there is a target I may miss that. So, all those says that there should be some concept of probability. So, I should have a concept of probabilistic thing. What is the probability? What is the probability? Probability that the radar will detect a specified target at a particular range. So, I will have to say it probabilistically. I cannot say always I will be able to give you the correct answer, but it should be such that the probability should be high, then only I will say that radar is a good sensor for detection. This is one thing. Another thing is that for a specified probability, what is the for a specified detection probability, that means suppose I have specified this detection probability, what is the probability that radar will falsely detect a target. That means, what is the probability of false alarm? So, these two, the first one, the probability that the radar will detect, this is given a symbol PD, probability of detection, and this one probability of false alarm, PFA. So, our model that R max, you see this model R max, that should be specified in terms of these two probabilities, PD and PFA. That means, what is the probability of detection, what is the probability of false alarm, based on that what is your maximum range, what is your all those parameters, that what is your unambiguous range, what is your receiver sensitivity, what is your RCS, etc. So, this we will have to now do, that we will do, this is called the actual statistical detection theory. This part I will now cover. Now, to do that, actually I need to develop the basics of this. So, for that what I will do now, I will make that again a simplified block diagram of the receiver, because this decision whether there is a target or not, that is taken at the detector in the receiver. So, for that is why I will now give you a model that I have an RF receiver mixer, because the RF signal is coming. So, I can say that RF signal, then mixer. After that we know that after mixing it has come to IF. I am assuming it may be 2 stage, 3 stage, but I am assuming 1 stage only. So, IF there will be an amplifier, then after that we know there is a second detector. Actually, these are all radar terminology, I will explain these. Second detector, and then there is a video amplifier, then there is a threshold detector. Who takes the decision? Sorry, let me call this decision. So, this is our now point that how this decision is taken. Now, here actually this video amplifier output, here I may have envelope detector. So, I am not specifying, or I can have phase detector. Based on that, the decision is taken that if it is above a threshold, we say okay, something is there. If it is below the threshold, we say nothing is there. Even though the actual case may be opposite, that suppose when I am saying there is a target, actually maybe noise is such high that I am falsely saying that there is a target. Similarly, suppose a target it is there, but it is for some time it is embedded in noise. So, I was observing noise. So, I will think no, it is noise, there is no target. So, I can miss that. That is why. Now, here, so this is my radar receiver block diagram, radar receiver. Based on this, I will build up the theory. So, now this second detector, actually this is also a actually diode stage, because after IF amplifier you have this diode in generally all the thing. Now, RF this mixer, this also employs diode, that is why it is called second detector or second diode, that is why the name came. And now, video amplifier, you know that this is the bandwidth falls in the video bandwidth, that is why the name video amplifier. So, this is an amplifier, and output of the video amplifier, there you are getting either the envelope or phase, and based on that, if you have an envelope detector, that is this second detector doing, envelope is getting detected. If you have a phase, then you have another mixer part, etc. So, and we assume that throughout this all these blocks, the maximum bandwidth, that is BIF. So, I will say that this I am assuming is the bandwidth of the whole receiver. That means, none of this is crossing this bandwidth. So, next page. So, I can say that when envelope or phase is above a threshold, I am writing Vt, in case of phase it will be some phase a thing. So, Vt, so detection decision made. So, this is a statistical decision, as I explained. Okay. Now, to have a answer to our that probability, that what is the probability that I will detect correctly or I will give you a false picture. For to understand that, let us assume that a case that this RF signal is absent, but we know that if signal is not there, even if the signal is not there, since it is coming to the free space. So, there are noises. So, noise has come to the antenna. So, there will be always some signal, something here that will be noise. Actually, in general this signal plus noise comes. Now, first I will take a case where no echo signal present. So, what is present? No echo signal present, but noise is present. So, that noise is getting passed through all these block diagram. Now, noise is, we are assume a white Gaussian noise, infinite bandwidth, but the moment is comes to this receiver of bandwidth BIF, its bandwidth also becomes the same BIF, it is not an infinite bandwidth anymore. So, it is a band pass noise, because this is an RF receiver. So, I have band pass noise Now, we know that any band pass signal or this noise can be broken into two parts, in phase and quadrature, two orthogonal parts, any noise can be taken. So, we will assume that this in phase noise is a random variable. Let me call that capital X is the random variable, and quadrature noise is also a random variable. Let me call it capital Y. So, they are random variable capital Y, and we assume both X and Y are Gaussian, zero mean, and identical standard deviation, because any noise or any random variable gets characterized by mean and standard deviation. So, let us call that their standard deviation sigma x. For x is having sigma x, y its standard, y random variable is standard deviation A. Now, due to this identical standard deviation, I can say sigma x is equal to sigma y, and let me call it sigma. Let me drop the subscript x and y. So, question is that suppose assume that in my this block diagram I have doing an envelope detection. Now, no signal is present, noise has entered, this type of noise I have characterized that. Now, what will be the envelope that envelope of this will also be a random variable. What is the probability distribution of that envelope? That means, what will be the distribution at the output of the video amplifier will get. This was a fundamental question radar people solved. Actually, this thing was solved by radar people. Rice actually solved that, and so now I will do that theory. These are the statistical part of the communication theory. You have probably done it in your communication classes, but I will revisit, because based on that actually we will have to modify our radar range equation. So, I can say that both envelope and phase at video amplifier output are random variable, because they are envelope of x and y two in phase and quadrature noise. Also the phase with respect to the phase of quadrature with respect to the in phase, that also is a random variable. So, if they are random variable, their character, one of the characterization is their PDF. So, what is the PDF, probability density function of x? Since we have assumed that they are Gaussian, we can easily write it. So, that will be Pxx is equal to 1 by root over 2 pi sigma out of this bracket e to the power minus x square, 0 mean, so nothing there, 2 sigma square. This I know. Similarly, I can write PDF of y, that will be P capital Y small y 1 by root over 2 pi sigma e to the power minus y square, again 0 mean. X may take any value from minus infinity to plus infinity, y may take any value from minus infinity to plus infinity. This is their probability distribution. Now, what is the envelope of this? So, I can write R is the envelope, that will be x square plus y square square root. This is the envelope. So, I can write envelope R, and phase phi, that will be tan inverse y by x. So, x and y are random variable. So, r and phi are also random variable. What we need to do, given this, I know the PDF of x, I know the PDF of y, what will be the PDF of r, what will be the PDF of phi. This is the problem. So, I can easily do this, because x and y are in quadrature. So, they are also independent. So, they are joint PDF. I can write independent. So, they are joint PDF is nothing but P x y is equal to 1 by product of those two, 2 pi, isn't it? Two independent variable, their joint PDF will be 1 by 2 root over 2 pi root over 2 pi, that is this, e to the power minus x square plus y square by 2 sigma square. So, this is their PDF. What is the joint probability? The joint probability that x and y are within an elemental area dx dy that will be probability that x is capital X, the random variable is having a value between x and x plus dx. Similarly, capital Y is having a value from y to y plus dx. This is probability, and if I know the joint PDF, I can write this probability. So, that will be P x y x y into x is varying from x plus dx. So, it is dx dy. This we know from our elemental knowledge of probability. Okay. Now, you see that we know that r and phi, they are dependent on x and y. R is equal to square root of plus square root of x square plus y square, and phi is equal to tan inverse y by x. Now, generally r phi we represent in 2D polar coordinate. So, question is this elemental area dx dy in Cartesian coordinate is equal to what elemental area in polar coordinate? That means, suppose in the Cartesian coordinate, I do not require this, 2-dimensional is enough. So, there I have, suppose this is x axis, this is y axis. So, I have an elemental area this, that means this is my dy and this is my dx, and this is my r, this is my dr, and this is my theta, and this is my d theta. So, what is the same elemental area in polar coordinate? Can I not say that this is r dr d theta in polar coordinate? So, these two are same elemental area dx dy in Cartesian coordinate and r dr d theta. This we know from our basic a thing. So, I can say that the joint probability in polar coordinate, let the joint probability distribution function in polar coordinate be P r theta r theta. Okay. Now, the probability that x is within x plus x dx, and y is from y to y plus dy, that will be then same as probability that r is from r to r plus dr, and theta is from theta to theta plus d theta. That means, I can write that this is joint probability distribution. Now, in probability will be same, because if the elemental areas are same, then probability is same. So, probability that x and y are within dx dy is same as probability that r and phi are within dr d theta. Same elemental area. So, I can write that P x plus dx y capital y plus dy, it should be equal to P envelope is r plus dr and theta these two should be same. So, these two probabilities should be same, because the areas are same elemental areas. So, then in terms of joint probability distribution, I can write that P x y dx dy should be equal to P r theta dr d theta. This is the outcome of this. Now, only thing is, what is dx dy in polar coordinate? Let me put that value P x y sorry, I know this area is r dr d theta is equal to P d theta. So, I have got the joint distribution r theta is nothing but, I have already written that. So, r by 2 pi sigma square e to the power minus r square by 2 sigma square, and only one thing, envelope cannot be negative. So, envelope is greater than equal to 0. Envelope cannot be negative. So, minus infinity to plus infinity, it cannot vary. It can vary from r is only taking. This is the joint probability distribution. Just you see, from the elemental knowledge, we can relate these two, and this is an note that this joint distribution is independent of the phase variable theta. That shows that the envelope and theta, they are completely independent, and so we can find out either the envelope distribution or the phase distribution from this joint distribution by properly integrating. That we will see in the next class. That will solve our problem. Thank you.